Hey, cool cats and kittens. Today we are doing section 4.5 here with real eigenvalues. But basically, this is just a continuation of what we were doing yesterday. So at the end of yesterday's notes, I had these 7 practice problems, which after today's lesson, I would encourage you to go and try in preparation for our quiz that's tomorrow. Our quiz will have the content that we've covered so far in chapter 4, including our work with eigenvalues and eigenvectors. And all 7 of these problems here are great practice for that. You by no means have to do them all. But basically what we're doing today is just a continuation of this work with eigenvalues, specifically when we get real numbers for those eigenvalues. So we will do an example of a 2x2 and a 3x3 just to help you out as you're working through these problems in preparation for tomorrow. So, couple of things to continue on from yesterday. We have our system of differential equations, y prime equals ay. And basically, we're going to say that our constant matrix A has eigenpairs lambda 1, x sub 1, lambda 2, x sub 2, all the way up to n number of eigenpairs, basically based off of, the dimensions of our matrix here. Our matrix is n by n, and so we should have n eigenpairs. Now, what we are looking for, and I mentioned this yesterday, is we want our eigenvectors to be specifically what we call linearly independent. Now, I did not use that terminology yesterday, so let's talk about that. Linearly independent is a linear algebra term that we use when we talk about matrices. What it means is that basically linearly independent means not parallel. Okay. Well, usually we talk about parallel when we're talking about lines. That is true. What it means when we are talking here about vectors and specifically our eigenvectors is that we don't get some x sub 1 that is just some scalar multiple of another eigenvector x sub 2. So this was the part, like I was saying, that I actually mentioned yesterday, is that when we find solutions for our eigenvectors, we may get eigenvectors, you and I, that are scalar multiples of one another. And that is okay. But what it essentially means is we got the same solution if they are, in fact, scalar multiples. So basically, going back up to here, and this is saying some different eigenvector, x sub 1 and x sub 2. So what we had with yesterday's example is linearly independent x1s and x2s. We do not want an x1 that is linearly dependent on x2 here. We want to make sure that they're not parallel to one another. Okay. So if that's the case, then our solutions, like we wrote out yesterday, where we take e to the lambda 1t times x1, the eigenvector there, and we continue on all the way down through our n eigenpairs, that will form a fundamental set of solutions if all of those eigenvectors are in fact linearly independent. Okay, so it's just an important distinction to make there in order to get to our fundamental set of solutions. If A is some n by n constant matrix and A has a full set of eigenvectors, that's a great thing. Then that means right there, this means fundamental set of solutions. If that is not the case, then we call A defective, which is kind of a sad word, but we are talking about matrices here, so I don't think their feelings are getting hurt too much. So we call the matrix defective if we cannot, in fact, get our fundamental set of solutions. And, we've talked a lot about what it means to have a fundamental set. So if you are not getting those linearly independent eigenvectors, then it might be that you have a defective matrix. So the examples I picked today are not defective. Just know you'll probably come across that in your homework somewhere. I picked ones today that we actually can solve. So we're going to form our general solution here and then solve our initial value problem. Again, just to be working through these so you get some good exposure to the types of problems that you're going to be seeing. So let's rewrite this in matrix form. This is already in a nice standard form for our system of differential equations here. So pretty quick to get this into matrix form, where we have 1, -3, 1, 5. All right. So there's y prime is equal to a times y. Now we also want to make sure in this case, because we have our initial value problem, that we take care of y of 0, which looks like this vector function right here. All right, so remember from yesterday that in order to find eigenvalues, we take the determinant of A minus the lambda identity matrix. So what that's going to look like for us, use some determinant notation here, is 1 minus lambda, -3, 1, and 5 minus lambda. So my determinant, 1 minus lambda times 5 minus lambda, and then plus 3 is equal to 0. So this one we will have to multiply out and see if it is factorable. So we get 5 minus 6 times lambda plus lambda squared plus 3 equals 0. So lambda squared minus 6 lambda plus 8 is factorable. And you factor it into lambda minus 2, lambda minus 4. So shortcut this a little bit. It looks like our eigenvalues for lambda will be equal to 2 and 4. All right, great. So once we find that, keep in mind now we are going to individually find eigenvectors for each of those eigenvalues. So lambda sub 1 is equal to 2. Using that, we go back to our A minus lambda identity matrix here. And it looks like our A minus lambda identity matrix then 1 minus 2, -1, -3, 1, and then 5 minus 2 gives me 3. All right. And then this is going to get multiplied by our eigenvector x sub 1 set equal to 0. So I can already tell that I'm going to have to do some guessing here, because if we notice row 1 and row 2 are just scalar multiples of one another. I can multiply row 1 by -1 and I get row 2. So that means essentially that if I use a little bit of elimination here, row 1 plus row 2, that I'm only going to get one equation that I can write here. I get x1 plus 3 times x2 is equal to 0. That would also be true using this. So the little bit of guessing that I have to do here is just using this fact. It has to be true still, but basically 3 times x2 is going to equal a negative x1. So whatever you use to make that true, besides the 0 vector, okay? We don't want to use the 0 vector because obviously that doesn't really help us here. So x1 or x2 has to have some value, and it looks like we probably can't just make one of them 0 and work it out with that. So I chose the eigenvector for x1 that looks like 3, -1. If I just make x2 equal to -1, then I can make 3 times -1 equals a negative x1, which would be 3. Okay, so that works for that one. Okay, and then we just have to make sure that when we do this with lambda 2, that we get a linearly independent eigenvector from that one. So it looks like A minus lambda identity matrix. I take 1 minus 4. That gives me -3. -3 there. 1. And then 5 minus 4, 1. And again, it looks like row 1 and row 2 are, in fact, scalar multiples of one another. And so for this one, in order to find x2, I'm probably going to have to do a little bit of guessing, but just kind of using my last row right here, it looks like x1 plus x2 is equal to 0. And so x1 is equal to a negative x2. Whatever fits that will work for us. And so I chose for my eigenvector for x2, I chose -1, 1. You could obviously flip-flop that. It would work just as well. But the idea is that here, x1 and x2 are linearly independent. That is good. That means that I will have a fundamental set of solutions here